Okay, here's going to be a longish video for class number 4. I kind of knew this was going to be a long class, and sure enough, I didn't get through all the material I wanted to, so I figured I'd make an accompanying video to try to help students who are a bit concerned or confused by the how fast we were going and how much stuff we tried to cram into one space. Here is the coordinate transformation section of this, recalling that from here we took, let's say that we had some other coordinate system which we're generically going to call it B1 and B2, and we want to change from IJ into B, or let's say that we're in B1 and B2 and we want to change to IJ. Either way, we're going to create a transformation matrix that allow us to go either way, either by reading columns or by reading rows. So B1 is already broken down for you right here. We have a X component, or an I component you could say, and a J component. If we did the same thing with B2, it would look like this right here. And I put hats on top, these little carrot hats. B2, let's switch over here, has a negative X component right here. So it's a negative, and if you drew the angle in here of the relationship between the IJ and the B1 and B2, you would see that it's the sign negative. So it's the negative, the sign here, and that's along the I. And similarly here, let's switch to green, we could see that we have a positive J, but it's a cosine, right? So it's a plus cosine theta of J. And what we end up with, if we write out these two equations here in this little matrix we've set up here, we get cosine of theta, sine theta, negative sine theta, and cosine theta. And one of the things we notice is that that it's almost symmetric. It's not quite symmetric because you have the negative sign in there. If we were going to write out the columns as equations, so right up above here, we have the rows written out as equations. Instead, if we wanted the columns to write out, we would say that I was equal to, and then we would go downwards. We'd say that it was the cosine of theta B1 right there minus the sine theta B2. And similarly for J, you would write that it's and reading downwards as a column, the sine theta of B1 plus the cosine theta of B2. And then using these right here, we would say in this generic setup here, or another problem, we have I and J. We're given IJ. We want to turn it to B1 and B2, which for some reason we've established as being down this direction. So what first we do is we can take our B2 and B1, and I'll use some other color here for the I and J, and looking at this, and this is a good trick, is to not draw them as 45-degree angles, right? You got to be careful so that you could see where make a small angle in there, or small-ish angle, somewhere in the 30-degree range usually works as a pretty good reference, and you could see that that angle is going to be the same as this angle right here. And so we set this thing up. Let's see, I guess I'll draw it right here. Nice to make a little grid. And I like to put the up. Let me put them in here. I like to put the I right here and a J right here, and then whatever we're moving over here. Of course, these things can be any coordinate unit vectors that we're trying to transform. Let's see, I'll go green here. So if we have B1 and we want to get the I part of it, it's going to be negative, right? It's in a negative I direction, and it's going to be the adjacent, so it's the cosine of theta. And similarly, for the J part of it, it's also going to be negative, right? Or maybe I'll go blue here. Let's go negative because it's going to be in this part right here, negative J. It's going to be the sine, right? Because it would be the opposite of this angle right here, where I'm drawing right here, but we're actually right over here on the axis right there, sine. Let's see, let's go switch to red here for the B2. B2 has a positive component here, and of course it's opposite from the angle right down there, so it's going to be sine, so that's got the positive I, positive sine theta of I right there, and then it has it too has a negative component, so it's negative cosine of theta. So if we so here's the coordinate transformation. If we want to try to now take for this setup here with theta is 75, we have, let's say, we can call this a force maybe. It's just some vector that now we want to turn it from I and J into in terms of B1 and B2. So what we do is we read now down these columns, right? So we turn I into B1 and B2. So we say P is equal to, take the magnitude of I, which is 4, and multiply it by the transformation, or minus cosine theta B1 plus sine theta B2 plus, and now we take the magnitude of J2 and do the column of J, and we find that it's negative sine theta B1 minus cosine theta B2. And we could collect all of the B1s and the B2s, and I stuck it in here. It's minus 4 cosine, I'll shove the 75 in there now, minus 2 sine of 75, that's B1, plus, all right, so now we can collect the B2s, and it's 4 times the sine 75 minus 2 cosine 75, and I didn't leave myself enough room for my B2 hat. Collecting all the stuff together, and 2.967 B1 plus 3.346 B2. All right, so there's a coordinate transformation. I should have just done this and limited it to this example. Let's see. All right, so the Crystal is standing chatting on her cell phone when her dog Derek suddenly takes off after a cat. Because she hadn't locked the retractable leash, the cord begins to reel out of the housing. That's like an R dot, isn't it? The cord is taut, and at that instant illustrated, the attachment to his collar is 3 meters to the right and 1 meter down, right? So it goes 3 meters here, 1 meter here. If Derek is running at 10 meters per second, so he's 10 meters per second, how fast is the cord coming out of the housing? When they say something like fast, they usually mean that's the speed. So they're only asking for the R dot component, really. Or you could look for the entire velocity. We could find all different parts of this thing. This is really a use of the coordinate transformation matrix, is a good use of it. I also said also find this, but because it's a constant speed going on here, both of these components are going to be equal to 0. So really just also find theta dot. So what we want to do is take our standard coordinates here, our I and j, and turn them into polar coordinates. Now the polar coordinates, the best one that we can use here is going to be ER aligned with the leash, and then orthogonal to it E theta right here. So what we're essentially saying is that this direction right here is where theta is being measured, right? It's being measured upwards right here. So in what we could do here is, I should say that this right here is how theta is being measured right here from this position right here. It's probably the easiest way to describe it. So we have this coordinate right here, where right here is theta, and right here is theta as well. So this is ER, and this is E theta. Making a coordinate transformation matrix. Would look like this right here. Take I and turned it in, or let me say I take ER and project it onto I. All right, so yeah, we want to, yeah, so that's going to be the sine. It's going to be the positive direction, so the sine of theta. And then ER onto J is going to be in the negative direction. It's going to be in the cosine of theta. E theta right here, we could say in the I direction, that's going to be positive, but it's going to be the cosine of that angle. And then in the J direction, it's going to be positive, but it's going to be, because it's opposite from the angle, it's going to be the sine of theta. So if we want to try to write V right now, originally is going to be 10I. If we want instead to turn that 10I into ER and E theta, we could say that it's going to be 10 times the sine theta ER plus cosine theta E theta. There, right? So we're going down in a column to try to get terms of ER and E theta. Plugging through there, we're able to find, so, and by the way, this theta right here, we're able to get that it's going to be the inverse tangent of 3, right? Because 3 is the opposite from that angle, divided by 1, right? And so we end up finding that it's like 71.57 degrees. So if we plug that back in right here to theta right here, we end up finding that we have 9.487 ER plus 3.162 E theta. So this becomes R dot, and so that's what we're going to talk about, how fast the leash is coming out. How fast is the leash coming out of the housing? Is going to be R dot. So it's 9.487, and these are meters per second, so that's the answer there. Here, this component is equal to R theta dot. So if we want to get theta dot, and I didn't leave myself enough room, if we get theta dot, we could take that 3.162 and divide it by R. By the way, we didn't figure out what R was going to be. It's just the square root of 3 squared plus 1 squared, right? Or if we get 3.162, noticing that that's interesting enough, right? That we're going to find out that it's going to be 1.000 radians per second, and that it's coming up this way right here, which makes sense, right? That this angle theta is getting bigger as the dog's running. All right, so I'm going to stop this here because I think it's office hours.